All right, now we'll talk about the second one, which is actually the big one, the one that will actually get used more often in applications and things like that. All right, so we start with this continuous function. Again, continuous is basically another way of saying everything's going to work out nicely. All right, if f of x is the antiderivative of the function I care about, then I have this statement, which is true. The integral from a to b of fx, or the area under lowercase f of x from a to b. All right, that's the left-hand side of this. And the right-hand side is the antiderivative. Let's not use that color, use the red. Antiderivative of f of x, which we call capital F of x, evaluated at b and a. So it's basically equating the area under a curve to some information about its antiderivative. So that's why before we had these kind of two separate notations, one without the bounds and one with the bounds. This one meant find the antiderivative. This one meant find the area. This is the reason we use the exact same kind of curly S notation, because they end up basically meaning the same thing. All right, finding the area is basically equivalent to finding the antiderivative, and then just plugging some things into the antiderivative. All right, so that's why we kind of practice both these separately, and now we're putting them together. All right, so when you'll see this kind of written in textbooks, and maybe when I write it by hand and stuff, all right, the fundamental theorem says I'm going to have to find out the antiderivative and then plug in these two different values and subtract them. All right, the way you write that in shorthand is I have my antiderivative, which is going to be called like f of x. I write a straight vertical line, and I put a to b. So this is basically shorthand for saying take b and plug it in, and then subtract, take a and plug it in. All right, which is that right-hand side of the fundamental theorem that was on the last slide. All right, so this is just a notation thing. If you see this vertical line, it just means plug these numbers in and subtract them. All right, so here we want to evaluate the integral from -2 to 2 of t squared minus 4 dt. Again, the variable name doesn't really matter. As long as this matches the dt, it just means take the area under the curve of this expression from -2 to 2. All right, so what do we have to do? The first thing we have to do is find the antiderivative. All right, so the antiderivative of t squared minus 4, it's going to be power rule. So you add 1 to the power divided by the new power minus adding 1 to the power is just going to be t. All right, so that's an antiderivative. Again, you always have the plus c. The nice thing once you start doing this fundamental theorem, the c is basically going to cancel out. You don't really need to worry about the c when you're doing this process. All right, then we go into the next step. Oops. We're going to plug in our top bound. So in this case, we're going to take 2 and plug it into this antiderivative we just found. So we're going to do 2 cubed over 3 minus 4 times 2. 8/3 minus 8. Then our third step, I keep using that color, even though it's not a good color. All right, plug in our bottom bound. That's going to be -2 cubed over 3 minus 4 times -2. And it's going to be -8 over 3 plus 8. And then I subtract these two things. So I'm going to take the top bound and subtract the bottom bound. 8/3 minus 8. Now I'm going to subtract -8/3 plus 8. The negative is going to distribute. I'm going to 8/3 plus 8/3 is 16/3. -8 minus 8 is -16. All right, so it's going to be 16/3 minus 16. All right, so you take the antiderivative, plug in your two bounds, and then subtract them to get your final answer there. And of course, you can get a common denominator and combine these into one answer. I'm just being a little lazy for the video to make you go a little bit quicker, but you can combine this into one single answer, but it kind of shows the steps that you have to do in order to evaluate this integral. And we'll do one more problem. All right, evaluate the integral from 1 to 9 of x minus 1 over the square root of x. So again, the first step was to find the antiderivative. And again, this is kind of the most difficult part of the process. There's a lot of different tools to find antiderivatives. We'll actually learn another one after we go through the section. But for this one, when you have this division, our goal is to get rid of the division as much as possible so we don't have to worry about quotient rules. And the way to do that with this problem is separate it out into two fractions. All right, so we split up that fraction over the minus sign, and then we're going to use the fact that the square root of x is x to the 1/2 in order to simplify. So x to the first divided by x to the 1/2, you subtract the two exponents, and that's x to the 1/2. Minus 1 over x to the 1/2, I can get rid of that fraction by making it a negative exponent. All right, so this is the same as what I'm starting with. So now I take the antiderivative of that. I have the antiderivative, which we call capital F of x. Add 1 to the power divided by the new power. So x to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. I'm going to put 2/3 there. All right, minus, add 1 to the power. I'm going to get positive 1/2. Divide by positive 1/2 is the same as multiplying by 2. All right, next step, I plug in my upper bound into that expression. And remember, the 1/2 power is the same as the square root, so it's going to be 2/3 times 9 to the 1/2 is 3. 3 cubed is 27. Minus 2 times 9 to the 1/2 is just 3. So we're going to do some simplifying. This is going to be, let's see, 27 divided by 3 is 9, times 3 is 18. Minus 6 is 12. All right, so if I plug in that first value, I get 12. All right, my second value is when I'm going to plug in 1. It's going to be a little bit easier because all the powers of 1 are just 1. That's just going to give me, right down here, 2/3 minus 2, which is negative 4/3. And the last step to get my final answer, now I take the upper bound and I subtract the lower bound. Again, I'm subtracting this negative, so it's going to end up adding 12 plus 4/3. And again, I'm going to be a little lazy and leave them as separate pieces, but ideally you would combine these into a single fraction and just have that one fraction as your answer. But again, this is good enough for now. We find the antiderivative of this expression by splitting it up into multiple fractions. Once we find the antiderivative, we plug in our upper bound, and then we plug in our lower bound and subtract those two answers. All right, so this is the general process we'll have to go through when we're finding areas that aren't just rectangles and circles and triangles. That's the basic idea. So we learned our two big kind of fundamental theorems are the kind of basis for the second half of a calculus course. The first one being if your function is defined using an integral, how do you take the derivative? And the more important one in terms of how much we're going to use it is the second one, that in order to evaluate an integral, you take the antiderivative and then plug in the two bounds. All right, so that's the kind of big things for the second half of the semester.